Hello.
Hello.
Yeah. Can you hear me?
Yeah.
Okay. So we'll continue with number theory. The
Uh-huh.
last thing that we had seen was basically residue classes, right? So different types of remainders that are obtained when you divide any number by another number. We
Yes.
saw that uh, let's say we divide a number by n,
Mm-hmm.
then the remainders can be anything from 0, 1, 2 till n minus 1.
Right. Yeah.
And these are all going to be called different residue classes,
Yeah.
different residue classes. And basically, all numbers can be divided into these n residue classes, which means that no matter what number you pick, it will either be in this set or this set or this set and so on, right?
Yeah.
They will either leave remainder 0 or 1 or 2 till n minus 1.
Right.
Now, what we will do is learn some basic modulo arithmetic. Modulo arithmetic means we sometimes think of, we don't do things like if, for example, x1 mod n is equal to r1. What we mean by that is x1 when divided by n leaves remainder r1. So basically we can say x1 is equal to some q1 into n plus r1, right?
Right.
So
Yeah.
x1 belongs to the r1 residue class mod n.
Mm-hmm. Yeah.
The number x1 will belong to the r1, some number here, r1 residue class, right?
Yes.
Similarly, also if x2 mod n is equal to r2, or you have x2 is equal to n q2 plus r2, then how can we combine these two numbers? So what will happen if I take x1 plus x2 mod n, right?
Yeah.
So we know x1 mod n is r1 and x2 mod n is r2. So technically now you can think that x1 is equal to nq1 plus r1 and x2 is nq2 plus r2. So x1 plus x2 will become what? nq1 plus q2 plus r1 plus r2, right?
Yes.
So it is obvious that if you divide x1 plus x2 by n, the remainder will be r1 plus r2, right?
Right.
Depending on whether r1 plus r2 adds up to something less than n or not, right?
Yes.
So it will be equal to r1 plus r2 mod n. In case r1 plus r2 adds up to something bigger than n, then you'll take that mod n and that will give you a smaller number itself.
Yeah.
For example, uh, we can take some number examples. So let's say n is equal to 36 and 1 second. Let's say R1 is equal to 5. So mod n. So basically some number which gives remainder 5 when divided by 36, right?
Yeah.
And similarly, you can have R2 is equal to 8, another number which gives remainder 8 when divided by 36, right?
Yeah.
So you will have the two numbers will be like this: 5 plus 36x and 8 plus 36y, right?
Yeah.
Now, if I have to take the combination, obviously you can see that it will be 36x plus y plus 13.
Right.
The sum of the numbers is this. When you divide it mod 36, obviously you can see that it is coming out to be 13,
Yeah.
which is the sum of the residues added together, mod n, right?
Yes.
So this is a basic property, but this example didn't give us the example that I wanted. We'll see that in different situations where the addition could have become bigger than 36, right? It is possible
Right.
that the addition could have become bigger than 36, but then you take that mod n, that will be your answer in that case, right? So the point is that this relation is true. And then similarly, if you have x1 into x2 mod n, in that case, you will end up getting R1 into R2 mod n. So even if you multiply the numbers, we can just write it as product of R1 into R2 mod n. So
Yeah.
we will see examples of this as well. Like, let's think of a number example where this will work. Any two numbers, like, let's say we are doing mod 5 and our two numbers x1 and x2 are 24 and 32. So x1 and x2 themselves are 4 mod 5 and 2 mod 5, right?
Yeah.
Let's multiply x1, x2 now. 24 into 32 will be 64 into 12, right? 4 into 3, right?
Yeah.
8 into 8 and 4 into 3. So 64 into 12, and that number is 640 plus 128. So 768, right?
Yes.
When you do mod 5, 768, answer is 3, right?
Yes. Right.
But when you multiply it, the remainders themselves, it is 8 mod 5. See, the product is becoming now bigger than this, right? 5. But that's still 3 mod 5.
Right.
So you can see that R1, R2 mod n is same as x1, x2 mod n, right?
Yes.
So technically we didn't have to multiply 24 and 32 and then find the mod n. It would be easier to just do 4 into 2 mod n, right?
Correct. Yeah.
So that's the important property. This is the same property as before. There it was addition, now it is multiplication. The property holds for both the operations, right?
Right.
Okay. Uh, do you understand what I've said so far?
Yes.
Okay, so try out this question. Uh, find the remainder when 7777 is divided by 13. Obviously, don't try to do it by the normal method, which is just direct division, right?
Yeah.
What I want you to do is try to think of some way to do it in a better way, because it is not likely that you will get an easy number here. You cannot do direct division all the time.
Okay.
Try to think of some better method which involves the modulo rules that we have just now seen.
All right.
What is the prime factorization of 7777? 7
Uh,
into, it will become
that-
1111,
yeah.
and 1111 you can try to prime factorize. That will clearly be divisible by 11. So it will be 11 into 101, right?
Yeah.
Okay, so my number that I want to find mod n is actually made up of three different numbers, right?
Yes.
So what the rule suggests is that I can x1 mod n, x2 mod n, if I know all of those values, right?
Right.
And x3 mod n.
Oh, and then you can multiply them.
And then I want to find out capital N is equal to x1, x2, x3. What is that mod n, right?
Right.
But it is enough to find out these values, right?
Yes.
And then I can just multiply these, right?
Yeah.
So our n is 13 here, right?
Yes.
So this is 7 mod n, obviously, because it's lesser than 13.
Yes.
This is 11 mod n, right?
Yeah.
And this is, when you divide by 13, it is 10 mod n, right?
Yes.
So the product of these will become 770 mod n, right?
Yeah.
Correct. Again,
Yes.
repeating the same logic again here also. This is 7 into 111 into, or 110. 7 into 110, right? So
Yes.
again, 7 mod n and 110 is 6 mod n if you think about it, right? Because 104 is divisible by n.
Right. Yeah.
Do you understand what I'm saying?
Yes. Yes.
So this will be equal to 7 into 6 mod n. So which is 42 mod n. And now
Yeah.
it is obvious that that is equal to 3 mod n.
Right.
N is 13 always.
Yeah.
So basically the answer is 3. And that is how you do it. Basically, we are splitting any number into its components, and each component's mod n we can find and then multiply those remainders.
Right.
Is it clear?
Yes.
Okay. Then 1 second. Right. Now, slightly harder. Suppose we want to find out the remainder, or we want to find out 7 power 7 power 7 power 7 power 7 mod 12. So that's what we need to find here. Okay. There are 4 sevens in a thing like this, powers like this.
Yeah.
One thing to remember here is that a power b power c is clearly not equal to a power b power c. This is not the same thing, right? Because this will give us a power bc.
Right.
What we have is a power the number b power c. B power c is clearly going to be bigger than bc.
Right. Yeah.
So don't make that mistake. We don't need to calculate this number. This number will be enormous, right? So
Right. Yeah.
think of some nice way by which we can do this whole thing in a better way, right?
Yeah.
Okay, I will not say the answer. You have to try it out. I will also uh, I'll also give you one more question. Prove that the number 117. This is the decimal expansion, and there are a lot of ones here. Uh, no matter how many digits of one, no matter how many digits of one, is not a perfect square. So there are some unknown number of ones here. We have to prove that no matter what it is, this number is not a perfect square.
Yeah.
Okay, now focus on these two questions. Take your time and try to think of whatever we have learned so far, we have to use it somehow, right?
Yeah.
Try it out. You have 5-10 minutes. I'll be back in 5 minutes to see.
Okay. Yeah.
Okay. So here, are you getting something?
I'm I don't know if you can say that like x to the power of x2 mod n is equal to like r1 to the power r2 mod n. I don't know if you can say that or not.
We can't in general say that,
Yeah.
but you don't need that actually. You need to think of powers of 7 first. So
Well, like
focus
so
on the
first,
number 7 here, and let's think of powers of 7, no, mod 12.
yeah.
7 power 1 is congruent to 7 mod 12, right?
Right.
7 power 2 is what? 1
7.
mod 12,
Yeah.
right? 7
Yes.
power 3, 343. If you think about it, it will become 7 square into 7 mod 12, right?
Right.
Do you understand by our property?
Yeah.
So it will be 7 square we know is 1 mod 12 and 7 is 7 mod 12, right? So this will
Yeah.
also be 7 mod 12, right?
Yes.
And you will be able to now show that all the powers of 7, 7 power 4 now will be 7 square into 7 square, right?
Right.
Which will be 1 into 1, which will be 1 mod 12, right?
Yes.
So can you see that powers of 7 mod 12 are always going to be 7 or 1, right?
Right. Yeah.
No matter what power you take, it will always be either 7 or 1.
Yes.
It will be 7 if it's an even power, an odd power, right? And it will be
Yeah.
1 if it is an even number power, right?
Right.
Do you realize that this pattern will keep repeating 7 1 7 1 and all?
Yes.
So any number is either even or odd, no?
Yeah. Right. Right.
So all we need to figure out is the power of 7 here, which is a big number, whether it is even or odd, right? This thing.
Right. Yes.
So think about it, 7 power 7 power 7 power 7, whether it is even or odd.
So the first one, it's gonna be,
What do you mean first one?
well,
We just
like,
need to figure out
yeah.
whether it will have whether it is even or odd.
Mm,
It is an obvious thing to figure out. No matter how many numbers are there, it is just repeated multiplication of sevens, right? Nothing else can
so,
come.
so it's just gonna be odd.
So it is obviously odd, right?
Yeah.
And if it is odd, what is going to be the mod 12?
Uh, is going to be 7 to the 7 mod 12.
The answer is 7 here.
Oh, okay, yeah.
Because powers of 7 we saw, the pattern is 7 mod 12 or 1 mod 12. Those are the only options. For even powers, it becomes 1 mod 12. For odd
Yes.
powers, it becomes 7 mod 12, right? And this
Right.
number that was in the exponent is clearly odd because you are never getting an even number at all inside it, right? It's just 7 repeated many times, right?
Right.
So the answer here is simply 7 mod 12, right?
Right. Yeah.
Okay. Then the next one.
For the second one, it was um, like no matter what number it is, it's like 1 dot 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 1 7. It's not gonna be a perfect square. Well, can't we just like list out like 1 to the power 2 is 1, 2 to the power 2 is 4, and if you just keep on doing that up till 9, you see that none of them end with 7. So then no perfect square is gonna have the last digit as 7.
Right. So that's correct. So only the last digit matters here, and all the perfect square, if you see, If the number ends with 0, you will see 0 square ends with 0. 1 square ends with 1, 2 square ends with 4, 3 square ends with 9, 4 square ends with 6, right? 5
Yeah.
square ends with 5, 7 square also ends with 9, 8
Right.
square ends with 4 again, right?
Right. Yeah.
And 9 square ends with 1 again. So the only possible digits that appear are these, right?
Yes.
So this cannot be a perfect square because it ends in 7, right?
Right.
So basically, we can state this in the way that any non-negative integer, non-negative integer ending in 2, 3, 7, or 8, right, is not going to be a perfect square.
Right.
There is no chance of it ending up as a perfect square because only the last digit matters here. So this number is therefore not a perfect square. Uh, so basically, the property that we are saying is last digit of n square. This L here denotes last digit of, right?
Right.
Last digit of n square is going to be the last digit of n square. Okay.
Yeah.
So this is the property that is satisfied. So last digit of n itself was something, and that square, if you check, you have to take the last digit of that number, right?
Yeah.
So in order to find if it was a big number, n was a big number, and I need to find the last digit of n square. Suppose I need to find last digit of n square. What I just need to do is take the last digit of n, L of n, square it, and then take the last digit of that, right?
Yeah. Right.
So just write down this property. This is useful. Uh,
Okay.
and remember that the converse of this is not true. Like just because the last digit is these doesn't mean it is a perfect square, right?
Yeah.
It is true in only one direction, that perfect squares will only have these last digits. But if the last digit is this, it's not necessary that it has to be a perfect square, right?
Right.
Okay. Uh, what is another way, a different way, another way to prove that a natural number is not a perfect square? That a natural number is not a perfect square. So another way to do it is if for the natural number n, there exists another natural number capital M, such that capital M square is less than n is less than m capital M plus 1 whole square, right? If you
Yes.
can show this, then obviously n cannot be a perfect square, right?
Right. Yeah.
Because it is between the perfect squares of two consecutive natural numbers, right?
Correct.
So this is a more common technique of proving that something is not a perfect square, right?
Yes.
However, this technique would not have been useful in our problem because our number was only not given properly. It was given with dot, dot, dot and all.
Yes. Right.
unless you know the number exactly, you can't really do this, right?
Right.
So that's why in that question we are using the last digit logic, right?
Right.
But here, this condition you can use if the number is given properly, you can try to prove it by this method. You have to find another number m for which m square is less than n and m plus 1 square is greater than n, right?
Right.
And then if n lies in between those two, then n cannot be a perfect square then,
Right.
right? Okay. The next problem is this one. Find the integers small n. Find the integers small n for which n square minus 4n minus 5 is a perfect square. So it is going to use the property that we have just now seen, the m square and m plus 1 square property, to try to do this, okay?
Right.
Because if you look at this, this should give you a hint of like a perfect square. It is close to n square minus 4n plus 4 and stuff, no?
Yeah. Oh, yeah, right, right.
So we can say for sure directly that this minus 5 is less than n square minus 4n plus 4, right?
Yes.
Which is n minus 2 square, right?
Right.
But for that property, we needed two consecutive squares, right?
Right. Yes.
So let's think of n minus 3 square also. So that is what? N square minus 6n plus 9, right?
Yes.
So if I can put it here, n square minus 6n plus 9 is less than this, right?
Mm-hmm.
Then I can say that this cannot be a perfect square, right?
Right.
By using the previous property, right? This
Yeah.
cannot be a perfect square then, right?
Yes.
So this part of it is always true. This part, this inequality is always true. No, there is no doubt in that, right?
Yeah.
But this inequality is not always going to be true, right?
Right.
Do you understand?
Yes.
So if you just try to solve this inequality, let's solve it. So n square minus 6n plus 9 is less than n square minus 4n minus 5. Let's find out what n. So n square will get cancelled and you will have 6n goes this side, 5 goes this side. So 14 is less than 2n, right?
Yes.
So 7 is less than n, right?
Right.
So this inequality is valid for n greater than 7. And this inequality is always valid, right?
Yes.
So the intersection of the solutions is that n greater than 7, right?
Yes.
So we can say for n greater than 7, this whole, the double inequality is valid, right?
Yeah.
But in that case, we cannot say that this will be a perfect square. It can never be a perfect square, right?
Right.
Because it is between two consecutive squares.
Yes.
Do you understand?
Yes.
Okay, great. But that still doesn't find us the n for which it is a perfect square, right?
Right.
Correct. Uh,
Yes.
so we do one more step. We say that actually n minus 2 square is equal to 2 minus n square also, right?
Yeah.
Do you understand? It's the same thing.
Yeah. Yeah.
So this inequality is still valid, but a consecutive square would have been now if 2 minus n square is here, I should have a 1 minus n square here, right?
Right.
Do you understand what I'm saying?
Yeah.
Two consecutive natural number squares, you have to put this number between them, right?
Yes.
Earlier, our numbers were n minus 3 and n minus 2, right?
Yeah.
But now I can also write it as 2 minus n and 1 minus n also, right?
Yes.
So let's do the inequality for 1 minus n square is less than this, right? Because that is not guaranteed yet, right?
Right.
So it will be 1 plus n square minus 2n is less than n square minus 4n minus 5, right?
Uh-huh. Yeah.
So 4n comes this side, 2n is less than, 5 goes that side, less than minus 6. So n is less than minus 3, right? Correct?
Yes.
And now the other side is anyway always valid. So the intersection is of the two solutions is n is less than minus 3, right?
Yeah.
So basically for n is less than minus 3 also, it cannot be a perfect square, right?
Yes.
So what we have done so far is we have excluded all the n's greater than 7 and less than minus 3, right?
Yes.
In those cases, it cannot be a perfect square, right?
Right.
So now we just need to check the numbers from minus 3 to 7, right?
Right.
Because the possibility is there that it could be a perfect square there, no?
Yeah.
So, but now it's a small set of numbers to check, no? Minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, 5, 6, 7, right?
Yes.
For in these cases, it is possible that it could be a perfect square. Other cases, we are already sure that it cannot be, right?
Right.
Are you understanding what I'm saying?
Yes.
So minus 3, if you put, for example, you'll get a 9 minus minus plus 12, 21 minus 5, 16. It is becoming a perfect square for minus 3, right?
Yeah.
Similarly, minus 2, if you check, you get 4 plus 8, 12 minus 5. No, it doesn't work for minus 2, right?
Mm-hmm.
And we just directly check it and you will get 4 of them which will work and others won't work. The numbers that work are minus 3, minus 1, 5 and 7. Out of these list of numbers, right? You can
Yes.
see that if you put 5, for example, you get 25 minus 20 minus 5, which is actually 0, which is fine.
Yeah.
These are the numbers that work. The other numbers don't work. And these are the numbers for which it can be a perfect square now. Right?
Right.
So notice what we have done. It's a intelligent way to use the property that if n square is less than n less than m plus 1 square, n
Uh-huh.
is not a perfect square, right?
Yes.
And here in this problem, we just did that. We had this number as a number to test. And then we can easily see that it's always less than n square minus 4n plus 4, right?
Yeah.
And we just, this was n minus 2 squares or 2 minus n square, right? So we just took the lower number here, right? So we had just had to see n minus 3 square or 1 minus n square, right?
Right.
And in both the cases, we got conditions because this inequality is not obvious. It's not always true, right?
Right.
This inequality is always true. So when we solved these inequalities, we got the condition n should be less than minus 3 or n should be greater than 7, right?
Right.
Which means in those cases, n will not, this number won't be a perfect square, right?
Right.
But we are left with only a small set of numbers other than those, right?
Yeah.
For which it is a possibility that it could be a perfect square. We just test those and we found our 4 answers.
Right.
Do you understand?
Yes.
Okay, fine. Now, the next problem is similar to the one problem that we did earlier, but now it is find the last 2 digits of A is equal to again the same number 7 power 7777, just like the previous time. We have to find the last 2 digits of this number. Earlier, we had to find the value of this mod 7, mod 12.
Yeah.
Hmm. By the way, should know that whenever you have to find the last 2 digits of the number, we just need to find A mod 100, right?
Oh, right. Yeah.
Anytime you have to find last 2 digits, it's basically finding the remainder when you divide by 100.
Right. Okay.
So somehow we have to figure out this number mod 100, right?
Yes.
Hmm. It's a nice way to do. There is a nice way to do it. Just have to be a little clever and patient. So
Isn't it kind of like the old one
yeah,
where
it
it's
is
like
kind of like that only.
7 power 1 is 7 mod 100, then 7 power 2 is 49 mod 100, then 7 power 3 is 43 mod 100, and then 7 power 4 is 1 mod 100, and then it'll just repeat?
Yes. So mod 100, any powers of 7, you will get a pattern of 4, right?
Yeah.
The pattern of 4 is when the number is of the form 4k plus 1, right? The
Uh-huh.
remainder mod 100, A mod 100 would be, or 7 power that mod 100 would be simply 7, right?
Yes.
mod 100 is 7, and then it would be 49, right?
Right.
If the number is 4k plus 2, right? Correct?
Yes.
The power is 4k plus 2, I mean. It will always be mod 100 will be 49, right? Because last two
Mhm.
digits will become 49. And then it will be 43, and then it will be 01, right?
Yeah.
That's the pattern. So all we have to do is think of the power here, the power, right? And
Yeah.
figure out which type of number is it, right?
Right.
Whether it is in 4k plus 1, 4k plus 2, 4k plus 3, or 4k plus 4, right?
Yeah.
So basically we have to find it power mod 4 we have to find, right?
Yeah.
If we know that, then we'll immediately be able to say what is going to be the remainder.
Yes.
Here we should write it as 0.7 actually, because the remainder when you divide by 100, right?
Yeah.
So now our job is slightly easier. We just have to focus on the power and find it mod 4. And you have to think
Yes.
in the same way again a little bit.
So then like 7 to the power 1, it's going to be like 3 mod 4.
Mhm.
And then 7 to the power 2.
Mhm.
Um,
Is 1
and
mod 4.
yeah, 1 mod 4, and then so on.
And then the pattern keeps repeating, right?
Yeah.
So odd powers, it is always going to be 3 mod 4, right?
Yes.
And even powers, it's always going to be 1 mod 4.
Right.
But it is obvious that the power here is an odd number, right?
Right.
This power can never be even, no? It's just repeated sevens.
Yes.
So since it's an odd power of 7, it will be 3 mod 4, right?
Right.
And if this is 3 mod 4, then the overall power is like a 4k plus 3, right?
Yes.
So the answer is 43.
Right.
Do you understand what has happened?
Yes.
So it's just like once you get the trick, it is not so hard. Okay. So
Okay.
you just
Yeah.
need to like be patient and figure it out, think a little bit.
Yeah.
Oh, okay. So I'll give you a couple of problems to try for the next class. And then next class we'll do those problems and go ahead with the theory. So
Yeah.
the next problem is show that a number written in base 10 by using just the digit 1 is a perfect square if and only if it has it only has one digit. Basically, we have to say that only 1 is a perfect square. Any other number with just ones, 1 1 1 1 1, it can never be a perfect square, right?
Yes.
So this is something that you have to try to prove. Then the next problem is uh, prove that there do not exist there do not exist four consecutive integers, each of which is a sum of two squares. Okay. prove that there cannot be four integers like this, each of which, four consecutive integers, each of which is a sum of two squares.
Yeah.
Okay, so these two problems you can try out as homework, and in the next class we'll discuss this and then go ahead with some theory, some more theory.
Okay.
The next class on Thursday will be our AMC discussion. So try out the
Yes.
papers, and the next week's class will be number 3.
Yeah.
Okay, fine.
All right. Thank you.
Bye.
Bye.